For one last thing we can do with partial derivatives, let's have a look at a kind of equation that we can write down now that we have partial derivatives available to us. A quick reminder about a topic you may have seen in Calc 2, or sometimes it comes up in Calc 2. So an ordinary differential equation is an equation that involves some unknown function y that is a function of an independent variable. So I could have written this y of x. So y is a function of an independent variable x, and also the derivatives of y. So this is an equation like this. dy dx equals 2y. So this is a strange equation because the unknown thing isn't just a variable that represents a number. It's a variable that represents an entire function, right? So the unknown here is a function and not just a number. And this equation expresses some kind of relationship between the derivative of the function and the function itself, right? You might have solved some of these kinds of equations. So here's an example, dy dx equals 2y. So a solution to this would be a function y that makes the equation true for all x values, right? It's not, to count as a solution, our function has to satisfy the equation not just for a few separated x values, but for all x values, or at least an interval full of x values. So to solve this equation, you might have seen some techniques for solving these kinds of equations in Calc 2, but one way of solving this kind of equation is just to guess. If the equation isn't too complicated, sometimes you can just guess solutions. So this equation says we are looking for a function whose derivative is twice the original function. So if it weren't for that 2, if we were looking for a function that was equal to its own derivative, you would probably be able to come up with e to the x, because that's a function that is equal to its own derivative. But that would be missing this 2, right? If we take this, so we might guess, hey, is this the solution? We could plug it into this equation. So on the left-hand side of this equation, right, if y is e to the x, dy dx is, well, it's e to the x. And on the right-hand side is supposed to be 2 times y, but I have poorly guessed, that y is supposed to be e to the x. And so then we can ask, okay, is this equation true? And the answer is no. This equation is not true. So e to the x is not a solution. So we need to to guess a solution, we would need to come up with a way so that taking the derivative spits out the original function but multiplied by 2. The way to do that is, e to the x seems like a good start, but we need the chain rule to spit out a 2, so let's put a 2 right here. Okay. Then you can plug this into our differential equation. So I've run out of room and I don't want to scroll, so let's do it over here. So we need dy dx. We are hoping that dy dx is equal to 2 times y. So if y is e to the 2x, the derivative of y with respect to x is e to the 2x, and then the chain rule spits out a 2. We want to check, is that equal to 2 times y, and y is e to the 2x. And yes, those are equal not just for certain x values, but for all x values. So yes, this is a solution. So y equals e to the 2x. That's a solution. Okay, so for this particular differential equation, it only has the first derivative of the unknown function y. It is possible to have second derivatives show up in your differential equations. So here's an example of a differential equation where a second derivative shows up. D squared y by dx squared equals minus pi y. Let me get rid of that pi, actually. Let's make things a little simpler. So of course, because there's a second derivative, this equation seems like in principle it should be harder to solve, and indeed second order differential equations that have second order derivatives are harder to solve in general. But this one is simple enough that if we just read it out loud, we can guess a solution. So we're looking for a function whose second derivative is the negative of itself. Okay, well, if you say that a few times and think about the functions that we know, can you think of a function that when you take its derivative twice, you get the negative of the function you started with? Yes, sine is such a function. It's not the only such function. Cosine is another function, and in fact there are more, but this does seem like it will work, so let's check if this is correct. So the second derivative of this function is minus sine x. And so if we take y and plug it in here, and take y double prime and plug it in there, is the equation true? Yes, both sides of the equation are the negative of sine of x. Okay, so this is what it means for a function to be a solution to an ordinary differential equation. Okay, so I haven't mentioned partial derivatives so far. The variation on the theme here is called a partial differential equation. A partial differential equation is, well, it's an equation involving an unknown multivariable function and the partial derivatives of that function. And the derivatives might be any order. Okay, so let's look at a couple examples. Partial differential equations show up all the time in physical sciences because so many interesting quantities in physical sciences depend on your location and also on time. And so when you describe how things that are functions of space and time change, you end up with partial derivatives all over the place. And so you get partial differential equations. So here's one example, the wave equation. The wave equation, it's for historical reasons, right? The traditional letter to use for the unknown function in the wave equation is u instead of f, so u of xt. And the wave equation is there's some unknown constant, or there's some constant c, which is turns out it describes the speed of the wave, and the wave equation is c squared times the uxx, and remember what this notation means is the second partial derivative of u with respect to x is equal to utt, and remember utt, that means partial squared u partial t squared. Okay, so this differential equation is called the wave equation. Another common differential equation that shows up in physical situations is called the heat equation. The heat equation is also a differential equation that, this should be a t here, differential equation that where the function has two input variables, one that is representing space and one that is representing time. And it looks a lot like the wave equation, except instead of having the second derivative of time, or the second derivative with respect to time, it has only the first derivative with respect to time. So this one, if we wrote it out using partial notation, it would be partial squared u partial x squared equals some constant times partial u partial t. This seems like a very small change to have only the first derivative instead of the second derivative, but in fact, this change has a huge effect on the types of functions that are solutions to these differential equations. If you study these sorts of things in a physics class, eventually you will see that the sorts of functions that are solutions are quite different. There's a constant in the heat equation, this constant A. It turns out it has something to do with how rapidly the material conducts heat, right? Okay. So, for example, here is a function, right? So u of x, y, so this y should be a t. Oh, actually, before we look at this example, I have written these differential equations with one space variable and one time variable. If you want to work in the full, four-dimensional space-time, you can write these equations with three space variables, x, y, and z, and then, of course, a time variable. They look very similar. Both of these equations look very similar. The only difference is you have one second derivative term for each space variable. So for the wave equation, for example, with three space variables, it's c squared u x x plus u y y plus u z z equals u t t. Okay, and then a similar thing for the heat equation. All right. Okay, so for example, here's a function u of x comma t equals sine of x plus sine of t. Is this a solution to the wave equation uxx equals utt? Notice I've chosen c equals 1 for this just to keep c out of our way. So how can we tell if this is a solution to the wave equation? Well, calculate these derivatives and see if they satisfy this differential equation. So let's calculate partial u partial x. So this would be ux. So taking a derivative with respect to x, the derivative of sine x is cosine x. And then the derivative of sine t with respect to x, well, sine t acts like a constant when x is the variable, and so the derivative of sine t with respect to x is 0. All right, now we can calculate uxx. That's going to be the second derivative of u with respect to x, so partial squared u partial x squared. So now we take our ux and take one more derivative with respect to x. So that's going to give us minus sine x. Okay, so now we know what the left-hand side of this differential equation is. It's minus sine x. Now let's calculate the right-hand side. So what is u sub t? U sub t, remember, is partial u partial t. And when we take a derivative with respect to t, this sine of x part goes away. So 0, because x is acting like a constant for the purposes of this derivative. And then the derivative of sine t with respect to t is cosine t. Okay, and then for our second derivative, u sub tt, that's partial squared u partial t squared. Take one more derivative, so that's minus sine t. Okay, and now we have to check, does this function satisfy this equation? Are these two things equal to each other? Well, no, they aren't. So this function is not a solution. No, it doesn't satisfy, this function does not satisfy this partial differential equation for some patch of the xt plane. Notice that these two functions, these are equal to each other for certain spots in the xt plane, right? In fact, they are equal to each other along the line x equals t, for example. But we are looking for a function that satisfies this differential equation on sort of a patch, by which I mean a two-dimensional region with some extent. I won't say exactly what I mean. We need an open set, basically, an open domain. But this line doesn't contain, this line where this differential, where these two things are equal, doesn't contain any patch of the xy plane, right? It contains a sliver of the xy plane, not a patch of the xy plane. And so this function is not, this function does not satisfy the partial differential equation. Okay, let's look at one more example. How about this function? And just for sanity's sake, actually no, let's keep this. Let's check if this is a solution to this wave equation. So cosine xt, cosine x plus 2t plus x minus 2t squared. Is that a solution to this differential equation? So, well, let's start calculating derivatives. I'll write things just with subscript notation this time. So u sub x, that's minus sine x plus 2t times, now we should be careful with our chain rule because we need to multiply by the derivative of the stuff inside here, and we are differentiating with respect to x for this, right? So we are taking the derivative of x plus 2t with respect to x, and that's 1. Okay, plus, and now we need to take the derivative of this polynomial part with respect to x, so do the power rule, 2 times x minus 2t, and then the power changes to a 1, and then also we need to, again, do the chain rule, multiply by the derivative of the stuff inside with respect to x, and that's 1. Okay. So u sub x is minus sine x plus 2t plus 2 times x minus 2t. All right, now we need a second derivative in the x direction, so uxx. Derivative of this first part is going to give us, let's see, minus cosine x plus 2t, and then times 1 again. But I won't write the times 1, right? The chain rule spits out a times 1 again, plus 2 times, and now we need to take the derivative of x minus 2t with respect to x, and that's 1. So this is minus cosine x plus 2t plus 2. Okay, so that's uxx. The left-hand side of this differential equation is 4 times that, so while we're at it, let's write down 4 times uxx. That's minus 4 cosine x plus 2t plus 8. Okay, now let's calculate the right-hand side of this partial differential equation for this particular function. So calculate our first derivative, u sub t. This is going to give us minus sine of x plus 2t times, and now we need to do the chain rule, right? Multiply by the derivative of the inside, but we're differentiating with respect to t now, so the derivative of x plus 2t with respect to t is 2. Okay, plus, and now take the derivative of this polynomial part, 2 times x minus 2t, and then this power changes to the first power, times, and now we have to do the chain rule again, right? Multiply by the derivative of x minus 2t with respect to t, which is minus 2. Okay, so altogether we have minus 2 sine x plus 2t minus 4 times x minus 2t. Okay, now we can calculate the second derivative in the t direction. Minus 2 cosine x plus 2t, and then don't forget the chain rule, multiply by the derivative of the inside. That spits out another 2 because we're differentiating with respect to t. Right, remember this is the derivative with respect to t of the inside. So that spits out a 2 minus 4 times, and then the derivative of x minus 2t with respect to t, that's minus 2. Okay. And then putting this all together, u sub tt is minus 4 cosine x plus 2t minus, so plus 8. Okay, now comparing 4 times uxx to utt, we see that, oh hey, these are actually the same, right? So this function, these are the same, I mean, they're the same for all input values of x and t. So in particular, they are the same for an open patch of the xt plane. And so is this function a solution to the wave equation? Yes. It is a solution to the wave equation. Well, I should say it is a solution to this wave equation. Right? If we change this number 4, it would no longer be a solution to the other wave equation with a different constant here. So which solutions you get depends on what numbers show up in the equation. It sounds obvious when I say that. Oh, I can't stop the video. Video, please stop.